The central limit theorem for sums allows us to take a random variable like x with any distribution and create a new distribution that happens to follow a normal curve. Let's start with a little bit of notation here. First, we're going to represent the mean of our original variable, capital X, using the Greek letter mu with a subscript capital X. We'll use sigma subscript capital X to represent the standard deviation of our original variable x. So those two parameters are coming from the original random variable with the distribution that we might not know, or maybe we know the distribution but we don't care. The new variable, that's the sigma capital X. This is a set of sample sums from the original data set capital X. So we take random samples from our original data set, calculate the sum, the total sum for that sample, and then we do that multiple times until we create the variable sigma x. Speaking of samples, the size of these samples used to create sigma x is n. So n will tell you how many values to take from the original data set x. The central limit theorem tells us that this new variable, sigma x, follows a normal distribution. The mean and the standard deviation can be calculated using three simple numbers. We need the mean from the original variable x, so we need mu sub x. We need the size of the samples that are being used to create the sigma x. And we also need the standard deviation from our original variable. So with those three things, we can figure out the parameters for this new variable, the capital sigma capital X. A little illustration here. We're going to take samples from our original data set. Each one of these samples will need to have the total sum computed on them. So we'll have a sum from each of the three samples that we've taken in this illustration. And then we'll use those sample sums to create our new variable, the distribution of capital sigma capital X. Capital sigma capital X has a normal distribution, and the center of that normal distribution is at the value n, our sample size, times mu sub x, the mean of the original variable. So the sample sums approach n times mu sub x as the sample size increases. Let's use these ideas in an example. Say we are working with an unknown distribution with a mean of 90, standard deviation of 15, and a sample size of 80 is drawn randomly from the population. We're interested in calculating probabilities about the sums. So we need to use the central limit theorem. First, we'll write down all of the information that's given to us. So the original variable has an unknown distribution, but we do know the mean is 90 and the standard deviation for this variable is 15. And that's what we need to be able to create our new variable, the capital sigma capital X, which is the set of sample sums. We're using samples of 80 values at a time, so we take 80 values and calculate the total sum, and that's what builds our capital sigma capital X. We need to know what the distribution parameters are for this new variable, so we'll calculate the mean by multiplying n times mu sub x, and we find a mean of 7,200. We also need sigma, which is the square root of n times lowercase sigma capital X, that's 15. So we'll do square root 80 times 15, which is also known as 15 times the square root of 80. I like writing my product like this so that I don't get confused if the 15 is inside of the square root or not. And at this stage, you could convert this into an approximation. However, if you want to do your calculations on a calculator, it's best to give the calculator the most precise values as possible so that it's able to produce the most precise values as possible. The distribution that we're working with then for capital sigma, capital X, is a normal distribution with a center at 7,200 and a standard deviation that's equal to 15 times the square root of 80. Now we're ready to answer questions like, find the probability that the sum of the 80 values is more than 7,500. First, let's translate that sentence into mathematical notation. The probability that one of these sums for our sample size of 80 is larger than 7,500. And I like to use visuals, so I'll draw the normal distribution for this capital sigma, capital X, labeling my center at 7,200, and then labeling 3 standard deviations above, as well as 3 standard deviations below the center. And we're interested in looking for the area that's at 7,500 and above. So I'll shade that in. It's the top end or the right tail. And I'm going to use my calculator to calculate this area to find that there is a probability equal to 0.0127, which is about 1%. So there's about a 1% chance that any one of these samples has a sum that's more than 7,500. We can also answer questions like, find the sum that's 1.5 standard deviations above the mean of the sums. To do this, we're going to interpret the question where we know we're finding a sum like sigma x, that's capital sigma x, that is 1.5 standard deviations above the mean. That's like saying a z-score of a positive 1.5. We're looking for the value of capital sigma x when the z-score is 1.5. We've done this before where we used an equation like x equals mu plus sigma times z, but we have to make a little bit of a modification here because we're not looking for an x, that was our original variable. We're looking for a capital sigma x. So we annotate so that we know we're calculating a value from our distribution, capital sigma, capital X. Plugging my numbers in, I can find that the sum we're looking for is 7,200 plus 1.5 times 15 square root 80. And that comes out to be about 7,401. So in this question, we were asked to find a sum that is 1.5 standard deviations above the mean, and we found it. That sum is 7,401.